Right, you can see on Canvas that this week's homework is due on Friday, so that there is no homework during the spring break. And the next one is going to be released on Wednesday when you come back from the break.
What days of spring break?
Huh?
What days of spring break? Still be working, you know?
Next week?
Okay.
It's for undergrad, right? Literally it's for undergrad.
Yeah, but like there is no classes during spring break. Yeah. All right.
Try not to show.
Okay. Yeah. So today is the real lecture. We start actually discussing chaos. So all the stuff we learned during periodic and even fixed point is going to be really tuned towards being useful for chaotic systems. All the concept of solving tangent equations, homogeneous or inhomogeneous tangent equations, of ergodicity, right? Of computing Lyapunov exponents, computing the covariant vector with regard to Lyapunov exponents, or they are actually just the eigenvalues and eigenvectors for fixed points. All of these are going to be useful for chaotic systems, as well as what we call statistical sensitivity of a long-time average the quantity with respect to perturbations to the system. So they'll all be useful for chaotic systems. But there is one thing missing before we seriously discuss real chaotic dynamical systems. That is what happens to the unstable Lyapunov exponent. Okay, so in order to really understand the whole picture, what we'll do first is to really simplify a typical chaotic system to its extreme so that we can only be concerned about the unstable Lyapunov exponent. We'll simplify, we'll just remove everything else. So this is using the Lorentz equation to demonstrate how we do the simplification, right? So from the attractor, we cut a slice. So basically we cut a slice through a Poincare section and extract what we call the Lorentz map. So this turns out to be a almost one-dimensional map that looks like that. And then we actually think about it as exactly a one-dimensional map. All right, so just a map like this. And you can see that this map actually captures the characteristic of chaotic system that has a positive Lyapunov exponent. Why? Because if you make any small perturbation, right, on the x-axis, no matter where you are on the x-axis, if you make a small perturbation, the resulting perturbation on the y-axis is going to be larger. All right. So the slope of this map has a magnitude greater than 1 everywhere. So that is the key behind why we actually want to do this abstraction. Abstracting this map out of the three-dimensional system actually removes the 0 and the negative Lyapunov exponent from the system. Okay, actually the negative Lyapunov exponent is abstracted out by treating this almost one-dimensional map as actually a one-dimensional curve. Okay, and the 0 Lyapunov exponent is removed by taking the Poincare section, right? So basically the time dimension gets out of the picture. So basically we obtain a map that can be thought of as a discrete dynamical system that retains the positive Lyapunov exponent. And of course it is not easy to evaluate this map because first of all, this map is not exactly 1D if you just capture the Poincare map. What we typically do is fit a certain rational function to approximate the map and use that as evaluation, but that's actually pretty cumbersome. So what we, for understanding the effect of the positive exponent, we further simplify the map from a nonlinear shape into this linear shape. Okay, so therefore, this map, what we call the tent map, actually has a derivative of the map exactly being either 2 or minus 2, depending on which side you are looking at. All right, and actually there is an even further simplification. Just to make the map has a derivative of just a 2. So basically, instead of looking at a fixed width in the real domain, we instead look at a periodic window in the real domain, just like our simplification for the periodic system, right? We actually think about a map between a periodic domain of 0, 1 to a periodic domain of 0 to 1. And the map goes up and then up again. So this is actually a continuous map, right? In the periodic domain from 0 to 1. That always we call the sawtooth map. All right, so basically you can write it as xn plus 1 is equal to 2xn mod 1, right? So that's what the map is.
So why doesn't have a negative value?
Why does what has a negative value?
Yeah, because we have a negative slope, right?
So the TED map has a negative slope on this side,
Yeah.
but the sawtooth map has positive slopes.
So it doesn't matter then? Means that being positive or negative doesn't matter? Yeah.
Right, so if you think about, it doesn't matter to the Lyapunov exponent, actually. Right, so because if you remember the definition of the Lyapunov exponent is the limit of t goes to infinity, 1 over t of the logarithm of the magnitude of the perturbation, right? The delta x t over delta x 0. So if you're on this branch of the TED map, the delta x would be flipped a sign, right, after one iteration, but the magnitude still increases by a factor of 2. So from the Lyapunov exponent point of view, it doesn't matter if the slope is positive or negative, as long as it is has a magnitude greater than 1, we get a positive exponent. Actually, either for the TED map or the sawtooth map, what is the Lyapunov exponent? Sorry? 1? So over every iteration, right, the delta x is magnified by a factor of 2, right? Okay, so over t iterations, it is magnified by 2 to the power of t, right? Okay, so this is for either the sawtooth or the TED map. This is actually like still the limit 1 over t log 2 to the t, right? Okay, which if you make the exponent out of the logarithm, it becomes multiplication. So it cancels with the 1 over t, so that's log of 2. So that's the Lyapunov exponent, and it's positive. All right. In this case, this is a discrete map, right? If you have a 0 Lyapunov exponent, that means the delta xt would remain the same size as delta x0, and we would have a log of 1, which is going to be 0, right? So anything that magnifies exponentially would have a positive exponent. All right, good. Okay, so this is the simplest chaotic system we can come up with, and we'll first of all, the first part of the lecture is going to be using this chaotic system to illustrate a few simple concepts. All right, so let's just how does the sawtooth map help understand the ergodic measure? So remember, like what is the ergodic measure? The ergodic measure is what is the fraction of time a typical trajectory spans, right, in the particular subset of the phase space. And in this case, the phase space is the space between 0 and 1. Okay, so what is the fraction of time a typical trajectory spans over a particular interval of this like this phase space. So this is actually a lot easier to think about if we convert the system from a geometric map into something algebraic. Okay, so just to think about the system, xn plus 1 equal to 2xn mod 1. So what is it algebraically? Particularly if you represent the xn just like how we represent a number in a computer, using binaries. All right. So of course, xn is in between 0 and 1. So if you use binaries, xn would be equal to 0 point something, right? Because it's between 0 and 1. And the only possible digits are either 0 or 1, right? So xn would be something like 1, 0, 0, 1, 1, 0, 0, 0, something like that, right? So it's going to be like an infinite series of digits. Now, when we're talking about a typical trajectory, right? Just to pick a random initial condition. So how likely is a random initial condition have a finite number of digits in the binary representation? It's going to be 0, right? So okay, so let me argue it from the like a proper measure theoretic point of view, right? So if you just throw a random point in this space, how likely is it exactly 0, right? It's easy to understand it's exactly 0, right? The probability is actually 0. Okay, so then how likely is it exactly 0.1? Again, it's going to be 0, right? So how likely is it going to be 0.01? Again, the likelihood is 0. So basically, for every finite precision number, the likelihood of you getting that number is exactly 0. Okay, and then remember, like for a measure theory, I mean for a measure to be a measure, for a probability to be a probability, it has to satisfy the countable addition property. So the probability, let me just call it mu, the probability of a countable union of let's say a certain series of sets is equal to the summation, the infinite series summation of the mu of AI. So let's just set the AI to be sets of single numbers, each one being a finite digit, be a number with finitely many digits, right? So you can actually list all possible numbers with finitely many digits in a series, in the infinite series that covers all finite digit numbers, right? And as a result of this countable addition property, right? So all finite digit numbers actually is a countable set. So this probability that you throw a dice and get a finite digit number is actually exactly 0. Okay, so essentially, if you analyze a random number in the real space, you're gonna find out that a random number with 100% probability, okay, is gonna have infinitely many digits. And the probability of any digits is more than that. The probability of any particular digits being 0 or 1 is actually 50%. There should be no bias towards either 0 or 1. Okay, and they're independent. A particular number being 0, right, would not make any subsequent or previous number being more likely to be 0 or 1. All right, so that's what a typical number in the real line looks like. Now think about what this map, the sawtooth map, does to a particular number. What is multiplication by 2 mean, like for a binary representation? It switches 1 zeros. Well, so what does multiplication by 10 mean? Like if you have a normal decimal representation, right? It shifts the whole series, right, onto the left-hand side by one place. So same thing as multiplication by 2 mean, right? In the binary representation, you shift the whole thing towards the left by one place. So this number multiplied by 2 would be 1.001100. So everything is the same except for the the point gets shifted by one place. And then what does mod 1 mean? Mod 1 just no matter what the after shift the digit, right? You just clear the binary, the bit before the binary point. Okay, so that's what the sawtooth map is doing. The sawtooth map essentially shifts and clears.
So mod 1 means that there is only one digit? Or I misunderstood. So mod 1.
Mod 1 means divide by 1 and take the remainder. Right, so that's what the map looks like, right? So if you look at the sawtooth map, if you just multiply by 2, the map would be like this, right? It goes all the way to 2. Okay, but our domain is between 0 and 1, being periodic, means 1 is actually the same as 0, and 2 is actually the same as 1, right? So you basically, this portion, the red portion, gets is the same as the black portion over here. Okay. Okay, so that's what the map is doing. It shifts and clears the 0. Now, if you think about a long trajectory, right? A long trajectory, basically, let's focus on each digit of a long trajectory. So for this digit, the most significant digit, what is the likelihood of the most significant digit being 1 over an infinitely long trajectory? Half, right? Because this got shifted after one iteration, the second digit becomes this digit. After 2 iterations, the third digit becomes this digit, right? So saying an infinitely long trajectory is essentially looking at all the digits and saying how likely the digits are 1, how likely they are 0. So basically there is half probability that the most significant digit being 1 and half being 0. That means the ergodic measure, right? This half of the domain versus this half of the domain is equal likelihood, right? Okay, how about the second most significant digit? What is the likelihood of being 0 or 1? Again, it's half, right? So that means, and it's independent of the first significant digit. What that means is that the probability of this measure on each of the 4 quadrants, right? Each of the 4 quarters is actually exactly half times half. And the same argument follows, right? So if you divide the interval into 4, 8, etc., right? Basically, it's going to be a uniform distribution over the interval 0 to 1. So, ergodic measure is uniform. Okay, any questions on that? So this is looking at a long time series. How about looking from the different point of view of ergodicity? How about looking at the evolution of an ensemble? So this is from the time point of view, right? A long time trajectory. Now let's look at from a evolution of an ensemble. So imagine I have an ensemble of points, and the ensemble of points does not have to satisfy the uniform distribution, but let's imagine it satisfy any distribution with one constraint, that the distribution is continuous. So let's imagine it has, actually, why don't we think about it as smooth, right? So it has a distribution like this between 0 and 1. So this is the probability of let's say the PDF function of x0. All right, the probability density function of the initial condition of this ensemble. So after one evolution, actually let's just consider what is the PDF of 2x0, and then we consider the PDF of 2x0 mod 1, which is PDF of x1, right? So what is the PDF of 2x0? What does it look like? Well, 2x0, of course, if x0 is between 0 and 1, 2x0 is between 0 and 2, right? And what does the PDF look like if you multiply the random variable by a factor of 2? It will look like the same, except for it's stretched in the x direction and squeezed in the y direction, right? So it's stretched in the x direction. Basically, for every x, the corresponding location 2x should have the same relative height, except for the integral has still to be the same. That means the height of the overall PDF is going to be decreased by a factor of 2. All right. So now, what is the PDF of 2x0 mod 1? You just cut the whole thing and stack this portion on top of this. So it's essentially you are taking this part and put it here, and this part put it into here, right? And you stack them up against each other, so you end up having something like this. Agreed? Now let's compare the PDF of x0 versus PDF of this is actually PDF of x1. And particularly, let's notice how the derivative changes. Okay, so what is the derivative of PDF x0 when you convert it into the PDF of x1? So what is the derivative? Let's just the PDF prime of 2x0. What is it like when you scale a function by a factor of 2 in the x-axis and squeeze it by a factor of 2 in the y-axis? What happens to the derivative? Decreases by how much? Well, not more than half, right? Simply by stretching it in the x-axis without squeezing the y-axis, how much decrease you get, right? 1/4, right, in total, because stretching you get factor of 2, squeezing you get another factor of 2. So this actually is a 1/4 of PDF of x0. All right, now after you stack it, at the maximum, you are going to be increasing. Just if you have a coincidence that by stacking the two parts of the PDF, the derivative are exactly the same, then you get a factor of 2 increase, right? But in general, it's going to be less than factor of 2. So the PDF prime of x1, actually the maximum absolute value of the PDF prime, the derivative of the PDF of x1, is going to be less or equal to half of the maximum over the PDF prime, the derivative of x0. Do you agree? Right? Okay, the stacking you cannot get by more than a factor of 2 by stacking part of the function with another part of the same function. Right? So PDF of x1 is basically the summation of this function with itself, but at different x locations. So what does that mean? That means for every iteration, the PDF function gets smoother and smoother each time by a factor of 2 or more, right? So after t iterations, the maximum possible derivative of the PDF function is going to be decreased by a factor of 2 to the t. There is an exponential convergence to a PDF that has no derivative. The only possibility being a uniform distribution, right? So again, the ergodic measure has a PDF with zero derivative. Okay, which is uniform. Uniform 0 and 1. All right, so this is going to be very useful when we actually extend the sawtooth map into actually a chaotic system with both stable and unstable directions. And we're going to see that it's actually a general property that a chaotic system is going to have a smooth distribution in the direction of its unstable manifold. So basically, in the unstable direction, there is a density, and the density is going to be smooth. Okay, so this is actually true for any system for which the unstable direction is actually uniformly expanding. By uniformly expanding, I mean like something like the Lorentz equation, where everywhere the derivative is actually greater than 1, right? Expanding map. So this is in contrast to some more complex chaotic system we'll study later, in which on average we still have a expansion. So the Lyapunov exponent is still positive, but there are regions where like even the unstable direction contracts, right? These would be the cases where you might not get a smooth distribution even in the unstable direction. But for right now, we'll first focus on the simplest case, for which the expanding direction, the unstable direction, is always going to be unstable, right? And yeah, we'll see like generally smooth distributions like what we get over here. All right. Okay, so let's actually file up our code and actually see if we can reproduce this smooth distribution that's proven to be uniform. And the answer is actually not always. Why? Because when we discuss, for example, a long time average of a trajectory, the assumption is that the initial condition, right, is actually have infinitely many digits, which is actually not the case in the computer. Like in the computer, whenever we generate even a random number, like we are actually using binary representation, right, which has finitely many binary digits. And let's see what we get. So if we have a x0, let's see, x is equal to random. I think we need to dot random. So we'll just have a random number, and then for let's say t, let's just take 100,000 steps. Let's also make a history is equal to zeros with t. History I is going to be set to x, while we'll just have x is equal to 2x mod 1. Okay, so that's our trajectory. And let's just plot a histogram of history with 101 bins and see what it looks like. Not uniform. Like all the numbers are concentrated at 0. So why is that the case? If you think about iterating this, right, shifting and clearing the 0 for a finite number of digits, what happens after you exhaust that finitely many digits by shifting? You get 0, right? You get 0 always. We've been shifting all the non-zero digits and clearing them, right? Ultimately, you do get zeros. So this is actually something we have to really be careful about in general chaotic systems, is that this is really the first indication that for chaotic systems, a tiny perturbation okay, a tiny perturbation even to the possible initial conditions, and we'll see also to the system itself, up to the numerical precision 10 to the minus 18 could change the statistics completely. All right, but we'll leave a more in detail discussion to later. So essentially, a tiny bit of perturbations, if just happens in a certain particular way, could change the statistics completely. So actually, any trajectories with so if x0 is equal to any I divided by 2 to the n, right? Then so leads to special trajectories. So what do I mean by special trajectories? Special trajectories are trajectories that whose long time average does not coincide with its ergodic measure. All right, so this is of course a special trajectory because its long time average is like this. All right, and can somebody else think about other special trajectories? If you start an x0 not with a finite many digits, could you still have special trajectories? Well, 0.111, that's right, but that's actually exactly zero. That's exactly equal to 1. Right, so you have like half plus a quarter plus eighth plus etc. The infinite series actually get you 1. So that's actually the same as this, right, which is 0. But that's a good start. Think about other things where like you have a certain pattern, right, as opposed to being completely random digits. Oh, special trajectories are trajectory whose long time average, long time behavior does not coincide with the ergodic measure. Okay, so I mean by long time behavior, I mean like if you have a long trajectory, right? What is the fraction of time that long trajectory spends within a set? For example, if we define the set to be the set between 0 and 1/2, all right. If you start the trajectory like this, at some point, all the xi's will be exactly 0, right? So the probability as t goes to infinity, that infinitely long trajectory spans within the set between 0 and 1/2 is going to be exactly 1. That's different from the ergodic measure. What is the ergodic measure? The ergodic measure is uniform, right? So the probability, like a random ensemble, or actually a typical trajectory spans between 0 and 1/2 is going to be 1/2. 1/2 is not equal to 1, right? So the long time behavior is different. So this is what I mean by special trajectories or atypical trajectories. Okay, can somebody think about a different trajectory that also does not have a uniform distribution?
I guess like an obvious generalization for what you're talking about is just any number with a sequence of pattern.
With the pattern, right? So can you think about the simplest pattern, right? 0. 1, 0, 1, 0, 1, 0, etc. Right? So what is this number equal to? I mean, if you are able to convert the binary to something like we can understand a bit better.
3/4?
3?
3/4?
3/4 is actually 0.11. Okay, so this is just think about it. So 0.1010 is equal to half, right? 0.0010 is equal to what? 1/8, right? Okay, so this digit would be 1/4. This is 1/8, and then the third 10 is gonna be what? 1/32, right? Okay, so basically you have the sum of these. The sum of these would be what? Half of 1 plus 4th plus 16th plus etc. Somebody do the math. 2/3, yes. All right. Okay. Good. So if you have a 2/3 and you follow, what is 2/3 times 2 mod 1? It's, well, 4/3 mod 1, you get 1/3, right? And what is 1/3 times 2 mod 1? 2/3. What do we get here? We get a periodic orbit, right? We get a periodic orbit. And this is actually true for any x0 equal to 2 to the n times 3. I mean, so any rational number, right, with a denominator equal to 3 times any power of 2. The 2 to the n is ultimately going to be cleared out by multiplying by 2. So you ultimately are going to converge to the periodic cycle between 2/3 and 1/3 and 2/3 and 1/3. Okay, and let me generalize it even further. Okay, so any x0 equal to a rational number n over m is going to be a period. It's going to ultimately get you into a periodic orbit. Why? Because first of all, like any factors of 2 in m is going to be cleared out, right? And then any the remaining m divided by any factor of 2, that denominator is never going to go away, right? It's always going to be a rational number that has a denominator of m with the factor of 2 removed. So the period can be something different, but it is going to go around periods, right? And it's not going to visit any irrational number. So it's going to be like special orbits, always. It's not going to be, the long time behavior is not going to be, it's not going to be any, the uniform distribution we have proved to be true. Agreed? So that actually makes it tricky to numerically simulate this stuff. For example, but one of the ways we have found it possible to actually reproduce the ergodic distribution is actually, instead of looking at the domain from 0 to 1, we look at it in the domain from 0 to some irrational number, like pi, for example. So instead of modulus 1 with modulus pi, and let's look at how that one looks like. Well, we do get something, right? Pretty close to a uniform distribution between 0 and pi, right? So we basically want to avoid any rational numbers as the upper end of this distribution. Okay, so in fact, so here we are doing floating point arithmetics, and it's very difficult to analyze the behavior. But if we are doing fixed point arithmetics, right, and we are using some prime number times the highest precision, of the fixed point arithmetic. It is actually exactly like a very simple form of random number generator, the linear congruent pseudo-random number generator. So this is there is some interesting correspondence between them. And let's actually, to make it even better, let's just do 1,000 trajectories, okay? And history is, and when we do a histogram, just coalesce these 1,000 trajectories, and we should see something very close to a uniform distribution by just averaging not just a long time long time, but also a many trajectories, right? So we do see this uniform ergodic distribution. All right, any questions? All right. Okay, so how does it help understand the Lyapunov exponents and vectors? So of course we are going to be knowing that the lambda is just going to be log 2, right? Because we are expanding by a factor of 2. And actually for a discrete map, if you have a contraction, like every step by a factor of 2, you would have a lambda Lyapunov exponent equal to minus of log 2, right? If you're contracting by a factor of 3 every step, you would have negative of log 3, right? So this is basically true for anything. And the vector is basically the direction, because we just have a one-dimensional map, there is really just the one direction, right? So it doesn't really matter over here. So, but this is going to be useful as we extend the sawtooth map into something known as the Baker's map. So here is the Baker's map. So the Baker's map, let me say a little bit more about the sawtooth map. So the Lyapunov exponents in a chaotic system is really like the rate at which information gets generated and the information gets forgotten gradually. So you can think about what the sawtooth map does, right? So for every iteration, the less significant bit in the binary representation becomes just one place more significant. So essentially, if you have a finite precision observation to the system, right? So let's say if you can only observe the first 18 bits, for example, or 64 bits, if you have a 64-bit representation, then for every iteration, there is one more previously unobservable bit gets shifted into view, right? So essentially, you have information generated, at least the observable information generated by this map, okay? And compare this to contrast this with a stable dynamical system. For example, xn plus 1 equal to xn divided by 2. Then every iteration, right, you are shifting towards the other side. You are forgetting one bit of information. The least significant bit got forgotten, right? Slowly, one bit by one bit. So that corresponds to a Lyapunov exponent minus log 2. So Lyapunov exponents can be really thought about how at least the observable information gets generated or gets into view, and how observable information gets forgotten, the rate at which it gets forgotten. So for example, if you have a Lyapunov exponent equal to log 4, then every step, every unit of time, you actually are generating 2 bits of additional information that's observable. If you have a minus log 4, then every iteration, 2 bits of information got forgotten. So you can really think about the Lyapunov exponents as rates. Now, the sawtooth map can be thought of as a positive Lyapunov exponent and a minus infinity Lyapunov exponent. Why is that the case? Because it actually forgets something that it doesn't forget things gradually. It actually forgets the most significant bit of the information immediately. Okay, so that it has the mod 2, but like basically the Baker's map actually fixes that by having a positive and a negative Lyapunov exponent. So a Baker's map is something we actually construct so that the unstable Lyapunov exponent is exactly the same as the sawtooth map. Actually, the unstable dynamics is going to be exactly the same as the sawtooth map, except for we are actually introducing another negative Lyapunov exponent where this a is greater or equal to 2. Okay, so how does that work? So basically the Baker's map is a map from xn, yn, so we're introducing another dimension into xn plus 1 and yn plus 1. And the dynamics on the unstable direction is exactly the same, so it's going to be 2xn mod 1, or in our case, let's just say mod pi, right? Because if you analytically, if you scale xn by a factor of pi over 2, right? These maps are basically equivalent up to a linear transformation variable. But yn plus 1 is going to be trying to capture the forgotten part of the map. So if you divide a number by pi and only captures the modulus, right? Only captures the remainder. Which part are you forgetting? You're forgetting, the integer part of the result, right? So basically, you are forgetting the integer part of the result. So let me just use the bracket to represent the integer part. And of course, you cannot just forget the previous yn. So what I'm going to be doing is add a previous yn, but I want to slowly forget it. So that means I'm going to be dividing it, not by a factor of 2, by a factor of a, right? So where if a is equal to 2, I'm just going to be dividing it by a factor of 2. So this is how we are introducing the minus log a part of the Lyapunov exponent, is this, right? Imagine you have a small perturbation, and the small perturbation is exactly in the y direction. So you are not changing x, only changing y. Then after one iteration, that small perturbation gets shrunk by a factor of a. 2 iterations, shrunk by a factor of a squared, etc. Right? So if you take the logarithm of the magnitude of the perturbation after t steps, you get t times minus log a, right? So that's why there is a minus log a Lyapunov exponent. But on the other hand, if the perturbation is not in the y direction but in the x direction, then there is no perturbation in y always stays the same, but x gets multiplied every time by a factor of 2. That's how the log 2 Lyapunov exponents gets into view. And this also helps us because we know exactly what the Lyapunov vectors are. So remember, what is the Lyapunov exponent? And it's so basically, okay, so let me just say Lyapunov exponent is the limit of t goes to infinity 1 over t of written it in a different way. It is the logarithm of the d phi, so that's the Jacobian, right? So d phi to the tth power, right? Starting at any location, at some location u0. This matrix Jacobian, right, which maps a small perturbation from time 0 to a small perturbation at time t times v, right? So this is the exponent, and just like eigenvalues, there is a map. There is each Lyapunov exponent is associated with a Lyapunov covariant vector. That's v. And actually, let me write it more precisely. V is actually a function of u0. So basically, we are going to see that in later studies, we're going to see that in general, dynamical systems, the Lyapunov covariant vector actually depends on where you are in the phase space. But in this particular case, we have lambda 1 and 2, and we have a v1 and 2. And the lambda 1, of course, is equal to log 2, and the corresponding v1 is actually everywhere equal to 1 and 0. Okay? This is a perturbation only in the x direction and not in the y direction. Lambda 2 is minus log a, and my v2 is everywhere equal to 0 and 1. Perturbation only in the y direction and not in the x direction. And what is my, this is because what is my d phi t? So the map between a small perturbation at initial to later is going to be exactly equal to 2 to the t and a to the minus t. And there is no off-diagonal terms. Right? You can basically just take this map and differentiate it with respect to x n and y n. You are going to get that.
In the definition of Lyapunov exponent, we have Jacobian.
Yes.
Which shows the direction of growth or decay.
Yes. Yes.
The other part is perturbation.
Yes. Yes. Right. Right. The perturbation is which direction you want to perturb, so that you get the particular rate of expansion and contraction. And in fact, this t, right? This t goes to infinity. It should actually be written more rigorously as plus and minus infinity, right? For the covariant vector to be properly defined. Because if you only think about the plus infinity, then any direction that contains a non-zero x component is going to grow like 2 to the t, right? Because ultimately any perturbation in the y direction gets diminished to 0, and the perturbation in the x direction actually dominates the whole magnitude. But why is v1 only why does v1 is 1 0 but not 1 with any y component? That is because this t can also be negative. T can also goes to negative infinity. And as t goes to negative infinity, this Jacobian is going to be taking a negative power, right? Which actually, as you evolve the perturbation backwards in time, okay, then the perturbation in the x direction actually gets decreased by a factor of 2 every backwards iteration. And the only way you can get a log 2, right, which in the negative in the limit of negative t, you have to have 0 perturbation in the y direction, because otherwise the perturbation in the y direction as you evolve backwards in time is actually going to expand and dominate the magnitude.
So why do we have negative side for negative value for time? It means that the backward.
Yes, it means backward. It means the so the d phi t when t is negative means the map between a small perturbation at time 0 to a small perturbation at time minus t. So what perturbation at time minus t do you need, right? So that the perturbation when propagated to time 0 would be equal to this.
But we don't have negative time, right? But for time.
What do you mean by we don't have?
Time is always positive.
Time doesn't have to be actually positive in value, right? Time is actually continuous going from minus infinity to infinity. So 0 means the current time. Minus time means the past. Plus time means the future.
Oh, okay.
So that's how we think about time in this context.
Okay.
Yeah. Right. So it is essentially with the minus t. So t goes to minus infinity means looking at the infinite past. T goes to plus infinity means the infinite future.
It's a new chapter. You opened it, right? Come on.
Okay. All right. Yeah. Any questions on this, particularly? To define the Lyapunov exponent, t can just go to plus infinity. But to define these covariant vectors, actually t has to t has to go to both plus and minus infinity for this to be unique, for the directions to be uniquely defined. Right? Does it make sense? Okay, so this is how the Baker's map is going to help understand chaos, and let's actually code it up and see what the Baker's map is doing. So what we'll do is we'll copy this, the same thing, because the x component is exactly the same as Baker's map, and let's say just the xy is going to be random with both the random x and y directions. Let's make it a little bit smaller. History is going to be then also has a y component. Okay, so here we have xy. The first component is going to be exactly the same as the sawtooth map, but the second component xy, first I have to capture the integer part of the division, right? So that's why I want to do the y component before I do the x component, because if I do the x component, it's going to be forgotten already. And then plus xy, the y component divide by a. So let me just set a to be. Let's first set a equal to 2 to see what we get. All right, so we get the history, but let's actually do it with hexbin. So basically, hexbin is a function that takes a histogram in 2 dimensions. Let me just x equal to history 0 and y is 1. So revel x, revel y, bins equal to 101. Let's see what we get. Oh, it's equal to x, y. All right. Okay, let's make a color bar. Okay, so let's just make sure we have the scale. All right. So what we see is that we do get a pretty uniform distribution, right? Within the whole space between 0 and pi, and from 0 to 2. So we'll just remember that in the take this as one fact, and we'll compare it with running it with a equal to 3. So basically something larger than 2, and see what the result looks like. It looks like that. So very far from uniform, right? Compare this with a equal to 2 to a equal to 3. Want to look at something more? Let's say we can do it again. Let's actually make a few figures. Actually, let's just duplicate these and make it a bit more. Equal to, instead of 3, make it 10. See what we get. All right, so basically we are increasing the magnitude of the negative Lyapunov exponent and make it more and more negative. So we see that. Can somebody summarize the difference between this distribution and the increasingly negative Lyapunov exponent and this one?
Y part is going to 0, while the X part just goes back to the sawtooth map where it's uniform.
Yeah, so the x direction doesn't seem to be changing much, right? It's all uniform pretty much in the x direction, right? But the y direction did change a lot, and it's getting, for example, if we make a equal to 100, all right, so what is, as a goes to infinity, what is the behavior in the y-axis? Yeah, it's getting less and less two-dimensional and become more and more one-dimensional, right? And I want to just remind you what I said about the sawtooth map, right? Without a y direction, it's like having almost like a negative infinity second Lyapunov exponent. So this is really almost the case if you make a equal to infinity. What happens is that every time we get the y component by taking either 0 or 1, right? They're basically having these two lines, but then I forget the previous one, right? So essentially what we get is just the distribution are just the two lines. So essentially we are, by changing a, we can go smoothly from a two-dimensional ergodic density, ergodic distribution, to a almost one-dimensional ergodic distribution.
Why was it for the second case? It seemed like there was a pattern in the strips.
Yes, for this case is the intermediate case, and that's something we'll discuss more carefully. All right. So just before we go into that, let me just take this. Remember, like the Lyapunov exponent is minus log a, and the Lorentz equation, as in the standard parameter range, has a negative Lyapunov exponent almost minus 19. All right. So for example, if we take e to the 19, right, and which is going to give us minus 19 as the Lyapunov exponent, we do see it's almost going to be a one-dimensional ergodic distribution. So that is actually why if you ever seen a movie about what the Lorentz attractor looks like, okay, it almost looks like a surface, right? It almost looks like two-dimensional. So how many of you have seen like the Lorentz attractor like in 3D, something that rotates? I mean, if you haven't, go search some YouTube videos. It looks just like a two-dimensional object.
Butterfly shape.
Yeah, butterfly shape. And that's also why if you take a Poincare section properly, right, you also get almost a one-dimensional intersection. So this is actually because it has a very, very negative Lyapunov exponent. Okay, but this is actually not general. So in general, even if it's actually very negative, it's just hides something like this in the details. So let's actually look at what actually happens analytically when we have a negative Lyapunov exponent, but it's not overwhelmingly negative Lyapunov exponent. Okay, so maybe let's go to here, right? In the case, let's first start with a equal to 2. Okay, and we have this domain from x goes from 0 to pi, and the y goes from 0 to 2, right? Because 2 is the maximum possible numbers you can ever get by looking at the Baker's map. So the first number here, right, is always going to be either 0 or 1. Okay, and the second number here, if the first number is 0, so if the previous y is between 0 and 2, right, then divided by a is going to be between 0 and 1, and the first number is always 0 or 1, so the summation can never be greater than 2. So that's why I put 2 over here. And then let's look at how, if I have a initial condition that's uniformly distributed over the whole domain, let's think about what is going to be the next iteration. So if x0 is uniform in this, then what I have is I'm going to be dividing the x-axis into 2 parts depending on if 2x0, well, let's just say x0 and y0 are both uniform and independent. That's how we say like we have a joint uniform distribution. Okay, so depending on 2x mod 2x mod pi is equal to 0, so that's this part, and is equal to 1 on this part, right? So for the first part, we are mapping, for the first part, what we have is x1 is equal to 2x, 0, and the y1 is equal to, well, the first part is going to be 0, so y0 divided by 2. So essentially, we are mapping the first part, so let me shade it into yellow. We are mapping the first part into this. We are expanding the x-axis by a factor of 2 and shrinking the y-axis by a factor of 2, right? So it maps the maps the left half of the plane into the lower half of the same plane. And then we are going to be mapping this part of the domain, right, into x1 is going to be 2x0 now minus 1, and the y1 is going to be 1 plus half of y0. So what does that mean? That means the y-axis, the x-axis is going to be expanded, but from here, right? I mean, another way to write it is it's going to be equal to 2 times, it's going to be 1 plus 2 times x0 minus 1, right? So basically, 1 is going to be the anchor. So we are, that's in the x-axis, we are expanding, but using, oh, okay. So I wrote 1 again, but I should be saying pi, right? This is minus pi, that's equal to pi plus 2x0 minus pi, right? Okay, so what that means is we are expanding the x-axis starting from pi, and the y-axis we are shrinking, but at the basis of 2, so 2 plus y0 minus 2 over 2, right? So it's the same. Okay, so what we are saying is that again we're expanding the x-axis and shrinking the y-axis, but using this point as the anchor. So essentially we are expanding the right half of the plane and put it over here. Agreed? Okay, so, and this of course keeps going, and if you map it further and further, then you are dividing this part and putting this part into here and this part into here, right? So every time it's really called the baker's map because this is similar to how a baker needs like flour dough, right? So you cut the dough in this way, and you squeeze this part into this, and you squeeze part and put it on top. Then you cut it again, right? And just keep doing the squeezing, right? So at the end of the day, the dough is going to be, if there is any non-uniformity in the dough in the beginning, this non-uniformity is going to be just really, really squeezed in the y direction and spread out in the x direction. So it'll be like any original features here is going to be extremely layered in after many iterations. All right. So this is what happens with a equal to 2. But what happens when a equal to 3? Why do we get the strange features in the y direction? Well, when a equal to 3, we have the same cutting in the x direction. So let's just also color the x-axis that way. But the stacking works a little bit differently. So the x direction is the same in the left part. In the left part, the x is the same, and the y part is going to be divided by 3, right? So if you draw the equivalent mapped dou, so from 0 to 2, instead of mapping the yellow part to the lower half, we map the yellow part to the lower third. So this is going to be the yellow part. And the green part, we are going to see that instead of mapping it to the upper half, we map it to here, right? So we map it to this part. So as a result, there is an empty gap in between them. Okay, so because there is an empty gap, when you map it further, let's see what happens when we cut this dou. Now, not with the uniform distribution, but with the distribution with the gap. What happens is that the left part gets mapped to, again, the lower third, right? The lower third. But it's not continuous. There is only a non-zero distribution within here. So when it gets mapped linearly, it's not the entire lower third gets filled. It's the entire third gets filled only in this part and this part. So it starts to get finer structures, right, over here. And also on the upper part, we also get the same finer structures over here. Do you agree? Okay, and it's actually might be easier to define the Baker's map a little bit differently. So instead of having, when a is equal to 3, right? So instead of having y1 equal to y0 over 3 plus x0 2x0 divided by pi, the integer part of this, I'm going to be multiplying this with a number such that the upper end of the green part coincides exactly equal to 2, right? What would that be? That would be actually times 4/3, right? So if I multiply this with 4/3, so basically the second number is either 0 or 4/3. If it's 4/3, basically I'm going to be and this number is between 0 and 2/3, right? So if this number is 2/3, this is 4/3, it exactly maps to 2, right? So essentially that helps me get rid of the requirement of looking at a gap up there. So essentially what I'm going to get is over one iteration, let's say the distribution of y, over in the initial distribution I get a uniform, right? And after one map I get a non-zero values only on the from 0 to 1/3, and actually from 0 to 2/3, and from 4/3 to 2. Now, after 2 iterations, I get a gap between each one of these. Okay, so after 2 iterations. After 3 iterations, each one of these actually again gets more finer structure, right? So can somebody tell me, like, after many iterations, what kind of set do I get for the distribution of y? not going to be uniform, right? So let me change this a little bit for this divided by a, and this doesn't change. This gets changed. Times a value that would make 2 minus 1 over a, right? 2 actually minus 2 minus 2 over a. So that is going to get us that's going to get us the whole range. And let me just let me also make another figure and do a histogram of rebel y. 101. Yes, it's like a fractal. This is a fractal, right? So with the gap in the 1/3, in the middle 1/3 of the domain, and then for each of the first and the last 1/3, it's empty again in the middle 1/3, and then for the first and last 1/3 of the first 1/3, it's also empty in the middle 1/3 themselves. So this is a set called the Cantor set. All right, so the Cantor set is obtained by, so y is in a Cantor set. All right, and the Cantor set is defined as the set of y's such that no matter actually let me say like half of y is in a Cantor set. That's how we define the standard Cantor set between 0 and 1, right? So let me just use another symbol. Is in the set of let me see, C, such that 3 to the any power of I times C mod 1 is not going to be instead of, let's see, 3 to the power of I mod 1 is not going to be in the middle. It's not going to be in 1/3 and 2/3. So what does that mean? That means that's for any I. So what does that mean? That means, of course, when I is equal to 0, right? So I'm just saying C modulus 1 cannot be within 1/3 and 2/3. That means the middle third is not allowed. Okay, and when I is equal to 1, that means 3 times C mod 1 cannot be in between 1/3 and 2/3. That means the gap over here, the gap over here, and the gap over here is not allowed, right? And then I is equal to 2. That makes like additional gap over here, over here, over here, over here is not allowed. So essentially, I would be only having a so essentially for every I, I'm removing 1/3 of the entire length of the existing length, right? From the from the previous set. Okay, so from a probability point of view, or from a measure point of view, right? What is the probability that you randomly choose a point and that lies within the set? Well, we can do the following analysis, right? So basically, after one iteration, starting from measure probability of 1, right? So that's basically the set that we randomly throw that covers the entire 0 to 1. And every time we are removing the middle 1/3, right, of all the contiguous pieces. So we are multiplying the length by 2/3. And then after another iteration, we have 2 segments, right? But we are removing the middle 1/3 of every segment. So essentially we are multiplying another 2/3, right? And another iteration, we are multiplying another 2/3. So keep multiplying. What is the resulting total length? What? It's going to be 0, right? We are taking the some number smaller than 1, taking the infinite power. So it's going to be equal to 0. So this is the probability measure of the Cantor set, right? Let me just call it C. It's going to be equal to 0. We are essentially distributing the y-axis, right, in a set that has 0 measure. And as a result, the measure of the whole, we can call it the attractor, right, or the whole support of the ergodic measure is actually equal to 0. Right? It's so this is the difference between this case and this case is the difference between how people define a conservative chaotic system and a dissipative chaotic system. Right? A conservative chaotic system is often seen in like a physical system that conserves kinetic energies. Like if you have a double pendulum, for example, that has no friction, right? You get chaotic behavior, but the kinetic energy is conserved, and you have a feature like this, where if you start from a continuous distribution, after a long time, the distribution of your solutions is still having a full, what we call a full dimension. That's like the possible locations after infinite time still occupies a positive measured space, while for dissipative chaos, after a long time, you start to get a measure 0 fractal object, like what we've seen here. Okay, so on Wednesday, we'll come back to this and start to analyze a bit more about this fractal object, including starting to look at its dimension, right? We know this object is not going to be dimension 2. Right? But it's not dimension 1 either. Dimension 1 means a line, right? So this actually had something in between 1 dimension and 2 dimension. So we'll discuss what is exactly the dimension, the fractal dimension, or the fractional dimension. Sorry? Actually, we'll actually look exactly at how this relates to the Lyapunov exponents. Minus the exponents. We will study. I mean, there is a interesting formula that we can actually calculate this, not just based on the negative Lyapunov exponent, but also on the positive Lyapunov exponent. All right. So it's the combination of these that's going to give you the fractal dimension. We'll also look at how the Lyapunov exponents are also related to the entropy of the system, for example, and then how this is going to generalize to a bit more complex chaotic systems. All right, so see you on Wednesday. Yeah, question?
I was just kind of thinking about this in regards, if you said it's a dissipated chaos, I was thinking about it in regards to turbulence.
Mm-hmm.
And I was wondering if this mapping has any relationship to like the energy cascade you did from turbulent systems.
Yeah, so turbulence is a dissipative kinetic dynamical system for sure, right? And it's very hard to analyze turbulence just by looking at the Lyapunov exponents because it's a spatially extended system, And the Lyapunov exponents actually depends not just on the dynamics but also on the spatial domain, right? If you look at the larger spatial domain, you would have more exponents to look at. So there is still some way to go between these, like the simple chaotic systems and turbulence, which of course is a dissipative system. Yeah.
Would we talk about turbulence in this class?
Yeah, but not till the very end. Yeah. Cool. Any other questions?
Also, another question. For the energy cascade in turbulent flow, we have a cosmograph universal law, which is -5/3.
Yeah, and nobody is able to derive that from a dynamical system point of view yet.
Okay. So I'm just curious if that number is related to Lyapunov exponents.
That's something we don't know, right? I think there could be a very deep relationship, but yeah, we don't know how that slope actually determines anything related to the Lyapunov exponents yet.
So do we only derive the slope from dimensional analysis? There's no other method?
That's the only way I've seen. I mean, so that's the easy way to derive the slope, right? So the real question is, can we infer something about the Lyapunov exponents from that slope? So that's the question I don't have any answer yet. Yeah.
But in the future you will have, right? I mean,
Yeah.
is it your field of study with that part?
Yeah, definitely. Yeah, so extremely interesting questions.
Because it's gonna open many doors.
Yes.